So we have this limit process to actually calculate a derivative, which gives us slopes of tangent lines. So we have a connection between the derivative and graphically what it represents. But it's real annoying to do. So we're going to start with coming up with techniques, and we're going to start with some basic differentiation rules and talk about derivatives in a sense of being a rate of change. So I'm going to go through our formal definition for a few particular functions, and we're going to see if maybe we can see a pattern that's going on and see if other stuff fits it. Then we're going to build on those different techniques to talk about when I take the product of two functions, when I take the quotient of two functions, when I have a function inside of another. How do I go about taking derivatives that way? So first and foremost, we're going to start with some simple functions, which are polynomials. We're going to begin with a constant function. So we're going to look at the function f of x equals c, and we're going to go through its definition with a derivative. So remember, the derivative of this function at any point is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So plugging in the fact that no matter what you input, the output is c, we get c minus c in the numerator, h in the denominator. So the numerator is always equal to 0. So this is 0, which means the limit is 0. So the derivative of the constant function is 0. No matter what you do, the rate of change of this is nothing. Graphically, if you have your constant function, it's just a flat line. No matter what point you pick, the tangent line is the line itself. It is flat. It has slope 0. Okay. Now let's try our identity function. So f of x equals x. Utilizing again our formal definition, the derivative is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So we take the limit as h goes to 0 of x plus h minus x over h. And luckily the h's cancel, or x's cancel. So that's the limit as h goes to 0 of h over h. That's the limit as h goes to 0 of 1, which is 1. So the derivative of x is equal to 1. And again, thinking of this graphically, you have your function. No matter the point I pick, the tangent line is just the line itself. If I can get this tool working nicely, not really, close enough. So the tangent line is the line. The slope of this line is 1, so the tangent line always has slope 1. Okay. Trying to now bump it up a bit because I still don't really see a pattern going on. Let's work with x squared. Its derivative then is same thing. I'm not going to write that difference quotient again though. So I plug in x plus h to give me x plus h squared minus our original function divided by h. Foiling that out gives us the limit as h goes to 0, x squared plus 2xh plus h squared minus x squared over h. So our x squareds end up canceling. So we get the limit as h goes to 0 of 2xh plus h squared over h. And then lots of h's, that cancels. One of those cancels. It is the limit as h approaches 0 of 2x plus h. Plugging in h is 0 gives us just 2x. So ultimately, the derivative of x squared is 2x. So to kind of notice a pattern that's going on between at least these three functions, this was a second degree, became a first degree. First degree became a 0 degree. This is a 0 degree, became 0. In all of these instances, really, this number popped out front and it gave us 2x to the first, so the power decreased. Same thing here, this pops down, decrease the power by 1. 0 pops down, gives us 0. So it kind of seems like the derivative of x to a power should be you bring the power down and decrease the power by 1. So second went to first, first to 0. If I have a third power, the 3 should be brought out front, give me a second power. But what happens if I have something that's not positive? Does the same idea hold for something more complicated, like a square root being a 1/2 power, or if I have x to a negative power? So we did a square root function similar to 1. Let's try going through the derivative of 1 over x. Okay? So if we have this function is 1 over x, then the derivative is the limit as h approaches 0 of f of x plus h. So that is 1 over x plus h minus our function all over h, which is not a pretty expression to evaluate. What I need to do is combine these to a single fraction. So I need a common denominator, which means I've got to multiply x and x plus h. This one, I need an x in the bottom, so I need an x up top. So this gives us the limit as h approaches 0. We'll get x divided by that piece minus x plus h, and that common denominator is x times x plus h. And this whole thing is divided by h. Okay. So simplifying this gives us the limit as h approaches 0. My x's cancel. We're left with negative h in the numerator. In the denominator, we have this expression, x times x plus h. We're dividing by h, so that's really the same thing as multiplying by its reciprocal. And luckily again, those h's end up canceling. So this is the limit as h approaches 0 of negative 1 over x times x plus h. Plugging in h is 0 now gives us negative 1 over x times x. So this derivative is negative 1 over x squared. Okay. So I've got the formula for a derivative. Let's see if it matches up with this rule. Does the power get brought down and is it decreased by 1? Okay. So I'm taking the derivative of 1 over x. You can rewrite 1 over x as x to the negative 1. So we would bring this power down, decrease the power by 1, so negative 1 minus 1 is negative 2. And x to the negative 2, flip it down to give you 1 over x squared. So you still get exactly the same thing. Okay? So really, if I'm dealing with any polynomial function, I'm just going to apply something called the power rule. If n is any real number, when I go to take the derivative of x to the n, the power gets brought down and it is decreased by 1. So this is one of our first fundamental rules that we're then going to expand on. So let's try an example first. Let's differentiate the function x squared times the cube root of x. But the problem is it is not in this form where I have x to a single power. So I need to get it in that form. Okay? So we're going to have to use some algebra to do some manipulation. We've got x squared times the cube root of x. That cube root you can rewrite as x to the 1/3. And when you go ahead and multiply two expressions with the same base, you add those exponents. So that would be 2 plus 1/3. And then I trust you can do that. That would give you 7/3 as a simplified fraction. So applying my power rule, this tells me my derivative is we bring the power down and then we decrease this by 1. So this will be 7/3. And if you do 7/3 minus 1, it will give you 4/3. Okay. So for right now, anytime you're taking the derivative, to be able to use power rule, it has to be x to a power. I can't treat these as two separate functions. Okay. The second rule we have is called our constant multiple rule. So all I've done so far is x to the n, but what if I had like a 6 out front? What does that really do? The constant ultimately changes nothing. So if c is a constant and f is a differentiable function, then if I want to take the derivative of a constant times the function, that constant can just pop out. You differentiate the function as normal. In terms of this prime notation, c times f, the derivative of that, would be the derivative is just applied to the function. Okay? So I want to show a little proof of this because it's not too bad that we can go through it. So we're going to let g be this function c times f of x. Then, if I want to take the derivative of g, using that difference quotient, it's the limit as h approaches 0 of g of x plus h minus gx over h. Plugging this into this expression gives us the limit as h approaches 0 of c times f of x plus h minus g of x divided by h. And now both of these have a c in common. Using our limit laws, that pops outside the limit, and we're left with exactly our expression for the derivative of f. So the derivative of this function is indeed the constant times the derivative of the function. Okay. The other thing that happens really nicely are known as our sum and difference rules. So if you have two functions f and g and they're differentiable, if you want to take the derivative of the sum of two functions, it's the derivative of each function individually. Likewise, if I subtract two functions, its derivative is the difference of their derivatives. So basically, if I'm dealing with this prime to take a derivative, the prime distributes across addition and it distributes across subtraction, which again just stems from your limit laws. So you're able to split things up. Okay. So now that we've got these tools under our belt, we can make our functions a little bit more complicated. So let's start with this polynomial where we have 5 times x to the 4th plus 7 times x squared. I'm going to add more steps than I necessarily need to start, but as you go through this, you're going to get quicker and quicker, and you don't have to do this process anytime. So if I want the derivative of y, I'm taking the derivative of this function here. And my sum and difference rules tells me I can go ahead and take the derivative of each individually. Okay. Then these constants make no difference. They pop out. And I want to take the derivative of x to the 4th, the derivative of x squared. Using my power rule, the derivative of x to the 4th is we bring the power down, decrease it by 1. Same thing, derivative of x squared, bring the power down, decrease it by 1. So you get 2x to the 1st. So this gives us 20x cubed plus 14x. Okay. Now realistically, again, you do not need to go through this process. You can jump right to here. This just shows you why you can go through it. So we'll do a simpler example, or an example where we don't put as many steps. Let's go ahead and differentiate this function. Again, remembering your square root is just a 1/2 power, cube root 1/3 power. So when we want to take the derivative, we go ahead and take the derivative of each thing individually. And we're just applying power rule. So the constant stays attached. Derivative of x to the 1/2 would be you bring the power down and you decrease it by 1. Same thing, bring the power down, so it'd be 5 times 3.2, decrease the power by 1. 6 times 1/2 is 3. 1/2 minus 1 is negative 1/2. If you do 5 times 3.2, it's going to give you 16. 3.2 minus 1 gives you 2.2. Okay. So let's try another example. Let's find the points on the curve where the tangent line is horizontal. And really, if you have a horizontal tangent line, your derivative is going to have to equal 0. So we want the derivative of this function to be 0. Well, I'm just going to apply a bunch of power rules. So we bring the 3 down, decrease the power by 1. Bring the 2 down, decrease the power by 1. Derivative of negative 12x is 12. Once you bring the 1 down, then it becomes x to the 0. Derivative of a constant is nothing. So my derivative is 6x squared plus 6x minus 12. I want to set this equal to 0, so I'm going to go ahead and take 6 out, which gives us x squared plus x minus 2. And then I can even factor this now. That's x plus 2, x minus 1. So if our derivative is going to equal 0, this happens when x is negative 2 or positive 1. So the horizontal tangents occur at the points negative 2, and you would plug this value of negative 2 into the function to see your y value would be negative 27. And likewise, if you plug 1 into this function, be 2 plus 3 minus 12 plus 1, your y value would be negative 6. You don't plug them into the derivative because the derivative is 0 at those points. Okay. All right. So now we were at two special functions, which are definitely much harder to go through. And so those two special derivatives that we had talked, or two special limits we had talked about before with these trig functions are going to pop up here, which is why they're important to us. So we want to find the derivatives of the sine and the cosine function. And we're going to start with the sine function. Really, the same process is going to be done for the cosine function. And you could look at the graphs to kind of compare these and see what happens, but sine and cosine are related. That's why they're co-functions, cosine. So their derivatives are also going to be related. So I want to go through this formal definition. My derivative is the limit as h approaches 0 of my difference quotient. So plugging that in, that gives me sine of x plus h minus the sine function. Now this is way complicated to work with, but maybe you remember some of your sum and difference identities. If you're dealing with sine of the sum of two angles, you can say that is sine of x cosine of h plus cosine of the other angle, sine of the other angle. And then minus sine of x all over h. Okay? So that's using that sum and difference identity to rewrite sine of x plus h. Now I want to manipulate it a little bit. We've got a sine of x here. We've got a sine of x here. I'm going to go ahead and split this a little bit to group those pieces. So I'm combining the two things that deal with sine of x with that denominator. This cosine of x sine of h is left over, so that's going to go in its own fraction. Okay. Now within here, I've got some like pieces. These both have a sine of x in common, so I can take that out. So that's going to give me sine of x times cosine of h minus 1 over h. And here, I'm going to split apart the piece so I have the h's together and the x's together as my input. And now, both of these, we're taking the limit as h goes to 0. So this has nothing to do with this limit. This has nothing to do with this limit. None of these involve h in any way, shape, or form. So they're treated like constants. So I can pop that sine of x out, pop that cosine of x out. And what we're left with are the two special limits that we needed. So cosine of h minus 1 over h, that goes to 0. This goes to 1. So ultimately, the derivative of my sine function, sine of x times 0 plus cosine of x times 1, derivative of my sine function is the cosine function. So this is our first important trig derivative. Derivative of sine of x is cosine of x. Okay. Now, if I go to do the derivative of cosine of x, you can really do the same thing. You're just going to use a different identity here for that sum and difference formula. The derivative of cosine will be negative sine. Okay. And you can map out pictures to kind of see that it's the opposite of each other, but these are our two first trig derivatives. In the next section, we'll talk about what happens with tangent, what happens with secant, with all of those other ones, but for now, we're just going to work with these. Okay. So let's try a few more examples. Let's find the derivative of this function, which is x squared plus x divided by x to the 5th plus 4 cosine of x. So before I can even start taking a derivative, I've got to simplify stuff. So first and foremost, I've got to go ahead and divide both of these pieces by x to the 5th, because I don't know how to deal with that right now. And then my cosine of x, that's fine. I can differentiate that. If we simplify x squared over x to the 5th, that's 1 over x cubed. This is still 5 over x to the 5th. And this is still 4 cosine of x. I want to write these as x to a power. So that's x to the negative 3 plus 5x to the negative 5 plus 4 cosine of x. So I'm now set up at a point that I can go ahead and use that power rule. I can also take the derivative of the cosine function. The derivative of this is we bring the power down, decrease it by 1, so that becomes negative 4. Bring the power down, decrease it by 1. Derivative of cosine is negative sine. So this becomes minus 4 sine of x. Okay. And you can clean this up if you want to. This is negative 3 over x to the 4th minus 25 over x to the 6th minus 4 sine of x. Let's try one more. Let's find the equation of the tangent line to this curve when x equals 0. So ultimately, we're looking for the tangent line at 0, and then whatever y value corresponds. So if you plug in 0 to this function, it would be 2 sine of 0 minus 5 times 0 squared plus 4. That y value is 4. The slope of the tangent line is the derivative evaluated at 0. So I've got to find the derivative. Taking the derivative of this, derivative of 2 sine is 2 cosine of x. Derivative of negative 5x squared is negative 5 times 2x. Derivative of 4 is nothing. So my derivative is 2 cosine of x minus 10x. And so my slope is, I plug in 0 to the derivative, that's 2 cosine of 0 minus 10 times 0, which is 2 times 1. Okay. And so the tangent line is y minus the y-coordinate is equal to the slope times x minus the x-coordinate. So that's y minus 4 is really equal to 2x. My tangent line is 2x plus 4. Okay. So we're going to still get more practice. We're going to keep using our power rule over and over and over again, the sum and difference rule. But we're going to take it up a notch in the next section, and we're going to figure out what happens when I multiply two functions. So instead here, what if I have 2 sine of x times 5x squared? What does that derivative look like? Knowing how to differentiate each individually.